We're going to talk about graphing logarithmic functions. This is 12.2b. If you haven't seen the previous 4 videos for Chapter 12, they were really important. If you become lost, it's because you needed to watch those videos, okay? They're linked in the description. A logarithmic function is the inverse of an exponential function, and one way to describe a log function is to interchange the variables in the equation y equals a to the x power to x equals a to the y power. You just interchange the x and y. And for log functions, we use the notation log base a of x. We read it log base a of x, or log a without the parentheses, see, of x. So it doesn't have to have the parentheses, but you usually will see it with it, okay? Now, the 2 important things I want you to remember and to write down, please, is a logarithm is an exponent, and y equals log base a of x means x equals a to the y power. That's really going to help you, okay? We're going to use this a lot. We use the symbol log base a x to represent the second coordinates of a function x equals a to the y power, all right? And if this is confusing, just stick with me because hopefully I'll clear all this up for you, all right? And the most useful log functions are those in which a is greater than 1. And the graph of this type of function is a reflection of y equals a to the x across the line y equals x. So that y equals x line is our diagonal line here, see? And the domain of the log function is a set of all positive real numbers. So you can see that y equals a to the x power, when we interchange the variables and get x equals a to the y power, this is a reflection across that x equals y line, isn't it? Now, if you've been with me through Algebra 1, you know my little card here. We have all these different names for x and y values. So now, aside from x being the domain, the input, the x-coordinate, that first set of members in the ordered pair or the abscissa, we could say it's a to the y power, or we could even say it's a to the f of x power. And the y is the range, the output, the y-coordinate, the f of x. It's the set of second members in the ordered pair, the ordinate. It's also the log base a of x, or a to the x power, all right? So let's take a look at this. We can graph y equals log base 3 of x. This equation is equivalent to x equals 3 to the y power. Because remember that really important rule? If it's a to the y power, then it's going to be 3 to the y power, see? Because 3 takes the place of a, see? And keep in mind that these are the same, all right? Whether it's the exponent is a y or if it's an f of x, it's the same thing, all right? And the graph of x equals 3 to the y power is a reflection of y equals 3 to the x power across the line y equals x, that diagonal line, okay? And we can make a table of values for y equals 3 to the x power and then interchange x and y. So we end up with a graph that looks like this. When we make a table of values to make this true, we come up with these values, and when we make a table of values to make x equals 3 to the y power true, we come up with these values. And if you look, they're inverses here, where we swapped. We've got an inverse of 2 here for x, but now it's the inverse of 2 for y. See that? That negative 1 is now for the y. See? That 1 for the x is now a 1 for the y. See? And it gives us a reflection when we plot those points. So the green line curve is y equals 3 to the x power, and the orange line is that y equals log base 3 of x. It's x equals 3 to the y power. See? Here's our diagonal line, y equals x. And the point 1, 3 right here, which is y equals 3 to the first power, is a reflection of the point 3, 1, or x equals 3 to the first power. Across the diagonal line, y equals x, all right? Now, you remember about zero exponents? Since a to the 0 power equals 1, for any a that doesn't equal a 0, the graph of y equals log base a of x for any value of a has the x-intercept 1, 0. Each logarithm is the inverse of the corresponding exponential function base a. And the inverse of a known function is easy to graph since it's the reflection across the diagonal of the original function. Now, keep an eye on this because we're going to do a lot of this in the next couple minutes, all right? We've got the log base a of x. It's the exponent for a that'll make a equal to x. Put it this way, if we have log base 3 of 9, what exponent can we have for 3 that'll make it equal a 9? Well, the exponent would be a 2. So log base 3 of 9 is 2. See? So let's do some more of those, and then we're going to talk about the domain of a log function written in set builder notation, okay? So we know that this is equivalent to this. So if we're asked what is log base 10 of 10 squared, well, we need this to be the base, and we need an exponent that's going to make it equal to 10 squared. Well, that's right in front of our face. It's going to be a little 2, isn't it? So it's going to equal 2. So just keep this in mind, this x equals a to the y power, all right? So what is log base 10, 1,000 of 1,000? Well, 1,000 is 10 to the third power. So that means 10 to the third power equals 10 to the third power. So what made it equal that? That little 3 exponent. So it's a 3. Let's try it again. Now we've got log base 10 of 1. Well, if 10 is the base, what exponent can we have for it that's going to make it equal a 1? A 0. So this is going to equal 0. Let's try it again. Now we've got log base 10 of 1/10. So 1/10, 0.1, is going to be equal to a to the negative 1. So it's going to equal negative 1. That's our exponent. Look at this one. We've got what is log base 2 of 8. If 2 is the base, what exponent can we give it that it'll equal an 8? A 3. 2 times 2 times 2. So it equals 3. What is log base 2 of 2? Well, if 2 is the base, what exponent can we give it that it'll make it equal to 2? Just a 1. So we know it equals 1. Now look, we've got a fraction. What is log base 2 of 1/4? Well, remember that negative exponent rule? There's going to be a link to integer exponents back in the first chapter of 1.7 in this description. If we have a base with a negative exponent, it's the same thing as having the quotient of 1 and a to that n exponent as a positive, see? To write it as a positive exponent, we make it the denominator, see? So 2 to the negative 2 power is 1/4. So the base is 2. We want it to equal 1/4. The exponent is negative 2, see? Let's try this one. What is log base a of a? Well, if a is the base, what exponent can we give it so that it'll equal an a? A 1. So it equals 1. How about what is log base a of 1? Well, if a is the base, what exponent can we give it so that it'll equal a 1? That's 0. Any 0 exponent makes that base equal a 1. See? It makes the whole thing equal a 1. So the answer is 0. So the domain of a log function written in set builder notation, there's going to be a link to the set builder notation that we talked about in chapter 3.1d. All right? And if you remember set builder notation, it's written like this with the braces, x, and then that straight line that stands for such that. And then it gives the description of how the set is built, okay, whatever rule it is. So the function of 3 to the x power would be all real numbers. And the function of log base 10 of x would be x such that, the set of all x such that x is greater than 0. See? And for log base a x squared, it's going to be the set of all x such that x is not equal to 0. And for log base 4x cubed, it's going to be the set of all x such that x is greater than 0. For log base 10 of 3x minus 4, that's going to be the set of all x such that x is greater than 4/3. See? When we divide each side by that coefficient 3, we're going to end up with the 4/3. All right? And then the function of log base 5 absolute value of x is the set of all x such that x is not equal to 0. All right? So hopefully that will help you write the domains in set builder notation, okay? We're going to continue on talking about log functions, and we're going to discuss graphing them more, and we're going to talk about how to convert exponential equations to logarithmic equations and vice versa. So this entire chapter is about this topic, all right? I'm trying not to make it a 30-minute video, so I'm breaking it into as little parts as I can. Links to those 4 previous videos for Chapter 12 that we've done so far are going to be in this description, along with 1.7 that talks about those integer exponents, those negative exponents, and 3.1d where it talks about set builder notation. I'm going to add this to the Algebra II playlist, and there's going to be a link to that playlist in this description. So I hope this was informative and helped you in some way. It's a very difficult topic for some people, and other people just grab it right away and they completely understand, because it's pretty much just like filling a formula and putting in the values into a formula and just working the formula, okay? So, I'll see you next video. Keep trying. I'm proud of you. Bye.